Hello and welcome you all to the 26th lecture of this NPTEL course where we are discussing the standard model of particle physics. And in the previous lecture we have started doing the calculation for a specific process. We are calculating the cross section for a specific process which is E minus tau minus going to E minus tau minus, and we have essentially gone through the details of what constitutes the Feynman graphs, what constitutes the rules which gives you the amplitude for the process, and now we are calculating the matrix element squared, which actually goes into the calculation of the differential cross section or the total cross section, so to say. Okay, so let's get started, and we are going to start from the point where we stopped in the last lecture. So what did we find out? We essentially find out that the matrix element square, the unpolarized matrix element square for E minus tau minus has to basically sum over all possible helicity combinations of the initial and final state, whereas in the initial state, because the polarization or the helicities have not been specified, so therefore we have to take an average. So for the two fermions which are colliding in this particular case, it will be essentially having a factor of 1/4. So that gives rise to this particular form of the matrix element square, which we called m bar square, mod of m bar square. So this basically means that I have taken an average over the initial state spins and summed over all the possible final state helicity combinations, and that gives rise to this particular form, that this is like 1/4 e to the power 4 by q to the power 4. So this is coming from the both the coupling and the propagator part, and then we have a sum over electron spin u e bar p3 gamma mu u e p1, u e bar p1 gamma nu u e p3, and this is something which we termed as L mu nu electron, because this only involves the electron spinors, so to say. And then sum over the tau spin, we have another L mu nu tau that we actually defined, which is u tau bar p4 gamma mu u tau p2 with u tau bar p2 gamma nu u tau p4. So therefore the matrix element square in general can be written as 1/4 e to the power 4 q to the power 4 L e mu nu and L mu nu tau. So this is exactly what we have to do. Now the next task is to calculate what exactly is there in this L e mu nu. Once we are able to calculate one of these parts, we will be able to guess what is the other part. So let's get started. So what is L e mu nu? It is essentially sum over the electron spin here, electron spin u e bar p3 gamma mu u e p1 u e bar p1 gamma nu u e p3. Now what I am going to do, that I am going to rewrite this expression in terms of the helicity components as well as the matrix components. Let's see how we can do that. So first of all, u e bar p3, let's assume that the helicity associated with it is r. So I have r, and of course I am going to sum over those helicities, or so therefore r is summed over r equal to 1 to 2, and the matrix component of this u bar is the j. Suppose this is the component that I am denoting by j. So u e bar p3 is essentially u bar r j. So r and s are the spin projection or the helicity indices of the initial state electron and the final state electron that are coming out, and then gamma mu doesn't have a helicity component, but that does have the matrix component, and the components are j and I. So the j is of course to take care of the j component that is sitting for the u bar spinor, and then u e p1, this will have a helicity component, let's call it us, and the matrix component will be ei. So you see the matrix components are nicely summed over u bar j gamma mu j I ui. Okay, and then let's similarly write the other part. So u e bar p1. So remember that because there is only one particle which is actually having the momentum p1, so if I am denoting the helicity state associated with that by s, which I have denoted in the earlier one, so like s, here also I have to indicate that by s. The matrix component I am denoting with a new notation, let's call it n. So it is u bar s n P1, and gamma nu that will have a matrix component n and m, and UEP3 this can be written once again. You notice that for UE bar P3 we had the helicity component denoted by R. So, here also I have to restore that notation, and the matrix component is of course m. So, that once again this is nicely summed up, that U bar n gamma nu n m U m, right. Okay. So, basically here the R and S, these are the helicity states of on which we have to perform a sum, and of course this J, I, N, M, these are matrix indices. So, once I have written in terms of components, I can actually rearrange them in the way that I do not have to restore the matrix multiplication explicitly, because I have divided them into component notation. So, what I am going to do, that I am going to segregate between the different helicity states, or rather sum over R equal to 1 to 2. If I do that, then what are the things that you have? So, you have URMP3 which is coming from this term. So, that is here URMP3, and then you have the U bar RJP3. So, that is what you have here, and then you have to do the sum over the helicity states S equal to 1 to 2. And what are the spinors that you have here? The spinor is here 1 and here 1. So, I am writing UISP1 U bar SN P1, correct, and then this gamma matrices component gamma mu Ji and gamma nu Nm, correct. Now, this expression that we have here is essentially something similar, something that we have already come across, right. So, this is essentially sum over the helicity states or spin states U bar. This is one of the completeness relation that we actually derived in the earlier lecture. So, can you tell me what exactly this is going to be? This is simply going to be P3 slash plus ME, because this is describing electron. And what will be the matrix component associated with it? The matrix component associated with it will be Mj, correct. This is Mj, and similarly here this will be essentially P1 slash plus ME, right. P slash M was when you summed over the completeness relation, sum over S US bar gives me P slash plus M. When you do for the antiparticle spinors like VS bar, that gives you what? P slash minus M. But here we have all the sum over the particle like spinors. So, this is P slash plus ME, and what will be the matrix component? You note this is I and this is N. So, this is I N, and then you have gamma mu Ji, gamma nu Nm. So, this uses the fact that we have this relation which we actually derived just in the last class. So, once again let me rewrite now these terms, arrange these terms neatly, and this is basically P3 slash plus ME, Mj component, gamma mu Ji, then you have P1 slash plus ME, and this is In component, and this is gamma nu Nm. So, that what does it mean? You see that this J indices is being summed over, I index is being summed over, N index is being summed over. So, this is essentially P3 slash plus ME into gamma mu into P1 slash plus ME into gamma nu, and it will be what component? The leftover components are M and M. So, this is the MM component, correct. Now, this NM components are the same. So, it is a repeated index which is summed over, right. So, what does it mean? It essentially means it is the trace of this whole matrix. So, this is the trace of this whole matrix, which is like P3 slash plus ME gamma mu P1 slash ME gamma nu and trace of it. So, with this now we are able to write the L mu nu tau part, which we already had in the expression. So, L mu nu tau part, you see that this was U tau bar P4 gamma mu U tau P2, U tau bar P2 gamma nu U tau P4. So you can imagine that these are the parts, you know, so these are the parts which is going to give you P2 slash plus m tau, correct? And this u tau P4, that is going to actually together with u tau bar P4 is going to give me P4 slash plus m tau, and the gamma mu and gamma nu will sit in between. So what we therefore have, we will have P4 slash plus m tau gamma mu, then P2 slash plus m tau into gamma nu and trace of it, right? So this is the L mu nu E, L mu nu tau. So in a sense, if you have to write the unpolarized matrix element square, this is 1 by 4 e to the power 4 by q to the power 4 trace of P3 slash plus m e gamma mu P1 slash plus m e gamma nu trace of P4 slash m tau gamma mu P2 slash m tau gamma nu. Remember, see that this is actually as a whole, this is actually a Lorentz invariant quantity, right? This mu index, nu index which is sitting over there, this is nicely, you know, balanced by the covariant mu and nu indices here, right? So that makes your that this is a nicely Lorentz invariant expression. Now most often what happens that in this kind of reactions, we actually work with a center of mass energy which is way higher than the masses of this particle. This is not necessary, but this is one of the conditions in which often we do these experiments with. So in that case you can say, okay, these masses are not significant for this particular reaction, or you can say that I can treat these masses me and m tau almost like going to 0. So in that case what we can do, that we can neglect these masses and these trace expressions simplify to some extent, and this becomes P3 slash gamma mu P1 slash gamma nu and trace of P4 slash gamma mu P2 slash gamma nu. Okay. So now it's the turn that we have to calculate this individual traces like P3 slash gamma mu, P1 slash gamma nu. इसको calculate करना पड़ेगा. तो let's start doing this calculation. The trace of P3 slash gamma mu, P1 slash gamma nu. P3 slash क्या है? P3 slash was essentially, P3 slash is something that you can write, you attach a Lorentz index, let's call it rho. This is P3 rho gamma rho. So that's what precisely I'm writing. So this is P3 rho gamma rho, gamma mu that was there, and then P1 slash I am writing as P1 sigma gamma nu. Now if you kind of mess it up by writing a gamma matrix which has same Lorentz index as nu or nu, that will actually spoil the whole calculation. So you cannot repeat it, because repeated indices have something very special. Those are repeated and summed over. So you please use a different Lorentz index for this P3 slash के साथ जो gamma matrix है, you write it in a special notation. Here I have written it like P3 rho gamma rho, and for the P1 sigma I have P1 slash I have written P1 sigma gamma sigma. So and these are nothing but numbers, right? P3 rho and P1 sigma. So I can bring them out of the trace, and so inside the trace what I have is trace of gamma rho, gamma mu, gamma sigma, gamma nu. Correct? Now you remind yourself of the trace relation that we actually talked about in the last class, that whenever this is a trace of 4 gamma matrices, then basically it will have 3 different terms. There will be first term where basically rho, this will be like 4 g rho mu g sigma nu, right? And then the next term will be g rho. So this term will have what? This term will have g rho sigma, g rho sigma mu nu, right? And the third term will be what? G rho nu, g mu sigma. right? So in a sense, now if you multiply with this P3 rho and P1 sigma, then you can see that whenever this rho is actually happening, so therefore this will become that, suppose G rho mu acting on P3 rho, which will give you P3 mu, and P1 sigma having contracted with G sigma nu will give you P1 nu, correct? This indices rho is summed over, so the nu index goes up. Okay, that's the free index that you have. On the second term, you have G rho sigma, and so the rho sigma when acts on P3 dot P1, that gives you basically P3 dot P1. So this is essentially minus 4 G mu nu P3 dot P1 plus 4 P3 nu into P1 mu when you multiply with the last one. Now this will help us to kind of write the next trace, which is actually this guy, right? So the next one was this one. So let's try writing that. So this guy will be what? So this will be 4 P4 mu P2 nu minus 4 G mu nu, both indices down, into P4 dot P2, right? And then what we'll have, that we will have plus 4 P4 nu into P2 mu. So this will be the expression for this particular trace. Now what I have to do? I have to multiply this guy and this guy. So that is what I am doing in this expression to do the matrix element square. So this will be 1 by 4 e to the power 4 q to the power 4, and I have written the expression for the traces here. And next let's do the multiplication. So you take the first term P3 mu P1 nu and multiply with each of these three terms. So when you multiply P3 mu P1 nu with P4 mu P2 nu, क्या आएगा? देखो, this will give you P3 dot P4, right? So this is P3 dot P4. P1 nu into P2 nu will give you P1 dot P2. Very good. Then P3 mu P1 nu with P4 nu into P2 nu क्या देगा? P3 mu and P2 mu, this has the same index, so this will be P3 dot P2, and this will be, the other one is P1 dot P4. The next term is minus 16, and G mu nu when acts on P3 mu P1 nu, that will give you P3 dot P1, right? So this is minus 16 P3 dot P1 into P4 dot P2. And now you take the next one, do the similar multiplication, write all the terms neatly. And if you do this algebra, you will see that many of these combinations gets cancelled. The one that will actually eventually remain will be this combination, that it will have 8 e to the power 4 by q to the power 4, P3 dot P4 into P1 dot P2, P3 dot P2 into P4 dot P1. Once again, I would like to remind you, these are 4 momenta. These are not the 3 momenta. So these are the 4 momenta associated with the initial state and the final state particle. P1, P2, P3, P4 are the 4 momenta associated with the particles which are scattering, in this particular process. Now let us use the Mandelstam variables which we introduced before. Now one of the Mandelstam variable is S, which is essentially defined by P1 plus P2 whole square is equal to P3 plus P4 whole square. Now what will happen, that if you do this P1 plus P2 whole square, this will give you P1 square plus P2 square plus 2 P1 dot P2. Now what is P1 square? P1 square 4 momentum square is essentially me square, and in this process, because we are neglecting the masses of each individual particles, so this will be simply P1 square and P2 square, which will give you me square and m square, both will be neglected. So you will remain with 2 P1 dot P2 or 2 P3 dot P4. So because your P1 square, P2 square, P3 square and P4 square are all the mass square of either electrons or the taus which are being neglected in this calculation, which will go to 0. Here I would like to also mention that therefore you see that when you take a massless limit, the cross section of an electron tau scattering and electron muon scattering are essentially going to be identical because the Feynman graph is the same. So the formula that we have come across, this matrix element square, that will be identical. The distinction could have been through the masses of these individual particles, but if you neglect the masses, then these cross sections are identical. However, if you take a scattering of electron with an electron, like electron going to electron, that is not going to be the same, because there will be another Feynman graph which will be contributing to that. I would like you to explore that possibility at home. Okay. So, but anyway, so what it turns out, so S is also a very important variable which is used in particle physics or collider physics a lot, and square root of S is what we call the center of mass energy of this collision. So square root of S, where S is P1 plus P2 whole square, is also defined as the center of mass energy of the collision. But in the massless limit, we can say that P1 dot P2 is equal to P3 dot P4 is equal to S by 2. Similarly, now let us construct the other Mandelstam variable, which is T, which is defined by P1 minus P3 whole square, which is P4 minus P2 whole square. So therefore, minus, once again, minus 2 P1 dot P3, which is equal to minus 2 P2 dot P4 equal to T, which gives rise to this point that P1 dot P3 and which is equal to P2 dot P4 is equal to minus T by 2. And the other variable that we didn't introduce here was this another Mandelstam variable that you can do, which is like P1 minus P4 whole square, and which will be P3 minus P2 whole square. This will easily stem out from the fact that P1 plus P2 has to be equal to P3 plus P4 from the energy momentum conservation. So this will be equal to minus 2 P1 dot P4, which is equal to minus 2 P2 dot P3 in the massless limit, right. So therefore, you can say that P1 dot P4 equal to P2 dot P3 is equal to minus U by 2. So essentially, you see that in the matrix element square, all these dot products of the four momenta can now be explicitly replaced by these Mandelstam variables S, U and T. So let us see what happens to these expressions. So tell me, what is the first expression? Let us take a look into that. P3 dot P4, P3 dot P4 क्या है? P3 dot P4 is essentially S by 2. What is P1 dot P2? That is also S by 2. So this first term is essentially S by 2 whole squared. What is the second term? You have the second term like P3 dot P2 into P4 dot P1. P3 dot P2 क्या है? P3 dot P2 is minus U by 2 and so is P1 dot P4. So this term is U by 2 whole square. Minus chala jayega because there is a square. So you can say that this expression then nicely turns into that, and also you remember that what was your Q? Q was essentially P1, the Q is the momentum which is carried by the mediator or the propagator photon, right, and that was P1 minus P3. So Q square, which is actually P1 minus P3 whole square, that is nothing but T. So Q to the power 4 is nothing but T square. So therefore, you have a beautiful and cute expression for this matrix element square, that this is 2 e to the power 4 by T square, A square plus U square. Okay, and yeah, so this is what we have already used, that Q square is equal to T. Now let us take this calculation further and let us stick ourselves to the center of mass frame. In the center of mass frame, what we can do, that we can say, what is the definition of the center of mass frame? Center of mass frame is essentially the frame where you say that these particles which are colliding, they are coming with equal and opposite momenta. So if I had to define the four momentum notation in the center of mass frame for these colliding particles, I will say that this guy P1 can be written in terms of E comma P, and P2 will be what? This will be E comma minus of P, so that I had P1 plus P2 is equal to 0. They are coming with equal and opposite momenta. So similarly, for P3 and P4, this will be E comma P prime and P4 will be E comma minus P prime. Now I cannot say whether P prime is equal to P, it will never be equal to, so therefore I have a different notation. Now you may have a question like why I choose all this E to be the same in all the cases. Now you can simply understand that this stems from the massless limit that we are actually working in. If we were not working in the massless limit, we couldn't have actually set this to be the same, right? I mean, of course, P and minus P in the center of mass frame has to be the same, but it is not necessary that we have to resort to the same energy E and E for the both of the cases. All right, but in the massless limit, this simplifies to this possibility. And we resort always that P1 plus P2 is equal to P3 plus P4, and this is actually true component wise, both for energy and the 3 moment. Now we say that P1 plus P2, therefore from this notation will be equal to what? Because this 3 momentum will cancel, so the P1 plus P2 will be simply equal to 2E, and by definition with the Mandelstam variable, this is square root of S, and you can simply say that this S is nothing but 4 of E square. Now what is T? T is P1 minus P3 whole square, and which is in the massless limit is minus 2 P1 dot P3. Now P1 dot P3, if you want to write it with the 4 vector notation, it's something like P1 mu into P3 mu, where mu is a covariant index for P3. Now therefore, if P3 mu E can be written as E comma P prime, then P3 covariant mu should be E comma minus P prime. Why? You remind yourself that G mu nu has this 1 minus 1 minus 1 minus 1. So once you actually bring the Lorentz index down into the covariant, say it picks up say additional minus sign. So therefore T, which is P1 mu into P3 mu with a factor of minus 2, becomes minus 2 into E comma P, and P3, which we defined as E comma P prime with P3 mu with Lorentz index down, becomes E comma minus P prime, and so therefore the product is 2 into E square minus P dot P prime, and P dot P prime from this arrangement you can say that this is the angle theta. So basically the P dot P prime is essentially nothing but cos theta, right? So P is along this direction and P3 is actually the angle with which this particle is being produced. So this is the beam axis, sometimes people say, and the angle which the produced particle subtends with, that is the theta angle, which you are saying that this is cos of theta. So therefore the T is simply minus 2 E square into 1 minus cos theta. Similarly, you can now exploit and find out that U variable, which is P1 minus P4 whole square, which is minus 2 P1 dot P4, that becomes minus 2 E square into 1 plus cos theta. There is a relative sign because P4 has a negative direction to that of P3, right? So therefore it will be, if this is 1 minus cos theta, this will be 1 plus cos theta. So with this we are now in a position to write actually the expression of the matrix element square which we derived here. So we have the expression of A square, and A square is essentially 16 e to the power 4, that is there. And what is U square? U square is going to be 4 e to the power 4 into 1 plus cos theta whole square, and the T square that was actually sitting in the propagator, which actually defines that it's a T channel graph, that will have an expression like 1 minus 4 e to the power 4 into 1 minus cos theta whole square. Now if you see that this e to the power 4, that gets nicely cancelled up and down, and so you are basically having the final expression like 2 e to the power 4 by 1 minus cos theta whole square into 4 into 1 plus cos theta whole square. Now we also know that in the center of mass frame, the d sigma d omega, the differential cross section, takes a form like 1 by 64 pi square S into mod of Pf star by mod of Pi star into the matrix element squared, right? So this is something that we have already calculated in the above expression, and here Pf star and Pi star, which are the final state particle momentum in the center of mass frame, they are essentially the same, so they also get cancelled, and what we therefore have, the differential cross section is 1 by 64 pi square S 2 e to the power 4 by 1 minus cos theta whole square into 4 into 1 plus cos theta. And once you integrate this d sigma d omega over the whole phase space, I mean d of cos theta spanning from minus 1 to plus 1 and d phi which spans to 0 to 2 pi, this is going to give you the total cross section for this particular process. And I would also like to mention that the total number of events in a colliding process is related to the total cross section with something called a luminosity. So this is what is called the luminosity of the process. It essentially indicates that what is the amount of particles that you are actually colliding with, right? So therefore, this is a machine specific quantity which we do not know unless some people tell you, and the cross section is however characteristic to the underlying process, and this is the cross section that you essentially get from this QED interaction to govern this. There is one interesting last point with which I would like to end this lecture, and that is basically that once you know this E minus tau minus collision to produce E minus tau minus, you see that for this particular process the electron current was defined by U E bar P3 gamma mu U E P1, which we have all been talking about. And similarly, the tau current that we had was U tau bar P4 gamma mu U tau P2. And if you remember that now if you actually change this collision to E plus E minus going to tau plus tau minus, where you know the electron is retaining P1 momentum, E plus is now having P2 momentum, tau minus is having P3 momentum and tau plus is having P4 momentum, then the corresponding electron current will be VE bar P2 gamma mu U E P1. Go back to your previous lecture and check if it is correct. J tau is U tau bar P3 gamma mu V tau P4, right? So now on the left hand side you have basically U, on the left you have basically U E P1, U E P1, U bar P3, U bar P3, U bar P4, U bar P4 on the left, and U P2, U P2. On the other hand, on the right hand side for E plus E minus to tau plus tau minus, what are the spinors that you have? You have once again U P1 which remains the same, then you have V bar P2 instead of U bar P3, you have V bar P2, then you have essentially U bar P3, right? U bar P3, and you have V P4, you have Vp4. So therefore, you can say that you can go from one diagram to the other, one amplitude to the other by the following replacement. What are these replacements? You replace P1 by P1, you replace P2 by P3, you replace P3 by P4, and you replace P4 by P2, but this is not enough. You actually also need to change from particle to antiparticle appropriately. Like you have P2 going to P3, but V bar is going to U bar, or U bar is going to V bar in depending on which direction you want to transfer. Or similarly, you have Vp4 going to Up2. That means a particle spinor is becoming antiparticle spinor or vice versa. So therefore, you can say that that basically paramounts to the transformation that P1 is going to P1, P2 is actually going to minus P3, and this takes care of the fact that this is now being replaced by the corresponding antiparticle. P3 to P4 is just a transition and no particle antiparticle exchange, whereas for the last one P4 going to P2 has to invoke a additional negative sign, which takes care of the fact that now this will actually flip to a corresponding antiparticle. So now what happens to this P1 plus P2? P1 plus P2, because P2 is replaced by P3. So this is the transformation which takes you from the left to right, from E minus tau minus to E plus E minus to tau plus tau minus. So therefore what you can say that P1 plus P2 is now becoming P1 minus P3, just because P2 is becoming minus P3. That basically means S, which is P1 plus P2 whole square, he is now becoming P1 minus P3 whole square. So S is becoming T. P1 minus P3, because P3 is becoming P4, so therefore P1 minus P3 becomes P1 minus P4. Now that basically means that T is becoming U, and P1 minus P4, because P4 is going to minus P2, is becoming P1 minus P4 becoming P1 plus P2, which means that your U, which was P1 minus P4 whole square, is becoming P1 plus P2 whole square, that is, it is becoming S. So then you know that, or changing U to T, T to S, or S to U will take you from E minus tau minus to E minus tau minus graph to E plus E minus to tau plus tau minus. So this was the process when we are actually doing this transformation from right to left. Right to left means E plus E minus to tau plus tau minus, but actually what we calculated was E minus tau minus going to E minus tau minus. So it's a reverse transformation. So T goes to S, U goes to T, S goes to U. So that's what we have to do. So this is what we have to do. So we say that if we just replace this, this is going to give us the matrix element square for E plus E minus to tau plus tau minus, and then let's try to write it from the expression that we had. This is 2 e to the power 4, this is 2 e to the power 4, T is becoming S. So this is A square. Inside the parenthesis, what we had essentially A square plus U square, right? So we had A square plus U square. So S is becoming what? S is becoming U. So this is U square. And we had also T square. We had A square plus U square. So U square is becoming T square, right? So this is essentially what we have. So this is the cross section for E plus E minus going to tau plus tau minus. Just I use the crossing symmetry to achieve this, and this is possible in the massless limit. Of course, in the massive limit this is not possible, but in the massless limit you can actually use this to get this. And you also note that in the S channel process, which is E plus E minus to tau plus tau minus, the propagator is minus g mu nu by P1 plus P2 whole square, which is 1 by S, and that is nicely reflected by the 1 by S square sitting in the expression. So following the same prescription that we did, if we evaluate this in the center of mass frame, the mod m square turns out to be e to the power 4 into 1 plus cos square theta, or the d sigma d omega, if you wish, this will be alpha square by 4 ECM square into 1 plus cos square theta. So this basically shows you that for E plus E minus going to tau plus tau minus or mu plus mu minus, this differential cross section when plotted with respect to cos theta between -1 to +1, this will be actually giving you actually a symmetric distribution. So this is the expectation that we have from the QED, that if QED the only process which actually governs this reaction, then this d sigma d omega should be symmetric. Let us write with some other color. So this is going to be symmetric, right? Because it's 1 plus cos square theta distribution. So this should be symmetric, something like this. But we will see that this is the point where actually experiment showed that this is indeed not exactly the same, and that's where we require theories beyond the quantum electrodynamics. But that's an interesting story. We are going to build it up slowly. But for the time being, what you are equipped with is to calculate any process related to QED using the sum rule, using the Feynman graphs and Feynman rules that we have constructed so far. So let's conclude here today, and we are going to carry it on in the next lecture. Thank you so much.